Japan, and also I'm visiting postdoc in ASIAA. So today I talk about covering factor that is key parameter for agent dust torus. In particular, we focus on agent polar dust we just discussed. That may be an additional key component for agent unified model. So we will discuss how the agent polar dust would affect the covering factor of SDSS quasars. So that is coming from a statistical point of view. So as just Dennis mentioned, X-CIGALE newly implements a clumpy torus model and polar dust model, which enable us to constrain polar dust emission based on the SED decomposition technique. So let's get started. So here I'll tell you about the following 4 topics. Let me first remind you of what covering factor is. The covering factor is defined as a fraction of the sky as seen from the AGN center that is blocked by obscuring material. Covering factor ranges from 0 to 1. As this value approaches 1, we can imagine a dusty torus like this. Also, this covering factor is often defined as a fraction of type 2 AGN, or a luminosity ratio of infrared to barometric luminosity, or a fraction of X-ray absorbed agents among the entire population. So in this work, we employ this luminosity ratio as an indicator of covering factor. As you may know, covering factor is expected to probe the structure of dusty torus, but an important question here is that what is a key parameter to regulate the covering factor, which is my topic in this talk. So let's see possible parameters on the next slide. So I think agent luminosity and black hole mass are possible candidates. As you can see this figure, covering factor decreases with increasing barometric luminosity or agent luminosity. This trend actually could be the case even for infrared, optical, or X-ray selected agents. In addition, some authors reported that covering factor may also depend on black hole mass like this. But recently, a few authors reported that key parameter determining covering factor is Eddington ratio rather than agent luminosity or black hole mass. This figure shows X-ray covering factor as a function of Eddington ratio for Swift-Butt local agent sample. We can see a strong dependence of covering factor, especially on higher Eddington ratio. But on the other hand, optical and infrared-based works claim that there is no significant dependence, as shown here. So question is, what is the reason of this discrepancy? One possibility is that uncertainty of infrared luminosity, because previous statistical works often used luminosity ratio of infrared to barometric as covering factor. Here, infrared luminosity should be came only from dusty torus, but in reality, infrared emission may be contaminated by other components, which I'll explain on the next slides. So this is polar dust. So recently, polar dust wind, probably driven by agent radiating pressure, has been reported as an ubiquitous contributor to the infrared emission. So I'm showing mid-infrared images of 9 local agents after subtracting the central PSF component. So you can see that extended emission that seems to be elongated in the direction of these green lines that are roughly correspond to the direction of polar emission, polar direction. So we can, for example, imagine that kind of picture for this source, for example. Also, some works are trying to model the SED of polar dust, as shown here. And also, they reported that luminosity ratio of infrared to barometric may depend on polar dust properties. So if the polar dust is common for agents, polar dust emission may be contributed to infrared emission that should affect the estimate of covering factor, which is the motivation of this work. So considering about background, the purpose of this work is to estimate dust covering factor by taking into account polar dust emissions. Again, in previous works, infrared luminosity may be contributed by polar dust emission, meaning that the derived covering factor may have large uncertainty. But in this work, we extract infrared emission purely from dust torus by using the SED decomposition technique, which enabled us to estimate more reliable covering factor, I guess. By using this sort of precise covering factor, we will revisit the relation between covering factor and AGN bolometric luminosity, black hole mass, and Eddington ratio. Alright, so next I'll tell you about sample selection, SED modeling, and spectral fitting to derive these quantities. Here I'm showing the flowchart of sample selection in this work. We used latest version of SDSS quasar catalog that has been recently published. In addition to its optical spectra, this catalog contains multiband photometry from SDSS, 2MAS, U-kits, and WISE. Compared to previous quasar catalog, this catalog also contains much more fainter quasars, like these red lines. Anyway, we first narrow down the sample to object with reliable spec Z, and then extracted object at redshift less than 0.7, because we aim to estimate black hole mass based on the same recipe by using H-beta line. As a result, 37,000 quasars were selected as a sample. For those quasars, we performed SED fitting and optical spectral fitting. After removing objects with sort of bad fitting, about 8,000 sources were left for correlation analysis. Again, for the SED fitting, we utilized X-CIGALE. As Dennis mentioned, and also summarized in this table, X-CIGALE incorporates clumpy torus model and also polar dust emission as AGN templates. Parameter ranges used in the SED fitting are summarized in this table. But here, let me remind that AGN emission consists of AGN accretion disk, dust torus, and AGN polar emission. Our SED fitting with X-CIGALE can extract only the torus emission that is directly used for estimate of covering factor. Again, we used these data for the SED fitting. In order to derive these quantities, we conducted spectral fitting to SDSS spectra by using quasar spectral fitting package, so-called QS-FIT. This code fits optical spectra simultaneously by taking into account such as AGN continuum and host galaxy component. By using outputs from QS-FIT, we derive black hole mass and bolometric luminosity by using sort of traditional recipes. Alright, so let me move on to the result and discussion. Here we will discuss following 3 topics. Also you can enjoy atmosphere of Kyoto. Anyway, here's an example of SED fitting and spectral fitting of 2 objects. So top panels correspond to the same object, say object 1, and also bottom panels correspond to same object, object 2. So purple, orange, and green lines correspond to AGN accretion disk and polar dust emission, and also AGN dust torus emission, respectively. And also some of these 3 components are shown in red line. We can see that polar dust emission seems to more or less contribute to total AGN emission. Also, right figure shows the result of the spectral fitting. Purple line are AGN continuum, and red line are AGN continuum plus AGN host emission. If we look at this purple and red line of object 1, we can see that AGN continuum is not enough to explain its spectrum, and it requires AGN host component, which is actually consistent with what is seen in the SED fitting. I mean, we require this blue stellar component. At the same time, SED and spectral fitting of object 2 consistently indicate that host galaxy component can be negligible for object 2. So in short, we conclude that X-CIGALE and QS-FIT consistently works very well. All right, so here I'm showing the dependence of covering factor on borometric luminosity, black hole mass, and Eddington ratio. We confirm an anti-correlation of those three quantities, which is consistent with previous works and recent works. Next, let me see how the AGN polar dust affects the correlation coefficient of dust covering factor and AGN properties. This is actually most important figure in my talk, which shows correlation coefficient of relation between covering factor and borometric luminosity, black hole mass, and Eddington ratio. If we don't consider contamination of polar dust emission like previous studies, we got these values. But if we do consider polar dust emission and extract only AGN torus emission to calculate covering factor, we got these values. As you can see, we find that taking into account AGN polar dust emission makes this anti-correlation much stronger. This is a very important conclusion. And also, in particular, the influence of polar dust component on the correlation strength may be significant for this Eddington ratio compared with other remaining properties. Also, we would say that no significant correlation between covering factor and Eddington ratio in previous works. That is maybe due to contamination of polar dust emission. Alright, so finally, let me discuss the consistency with X-ray based works. As I said, we confirm that anti-correlation of covering factor and Eddington ratio for SDSS quasars. But you may notice that correlation strength we get here is much weaker than what was reported based on X-ray data. So what causes this discrepancy? One possibility may be difference in redshift between two subsamples. Rich et al. Targeted really nearby agents with a median redshift of 0.04, but we focus on much higher redshift up to 0.7. This figure shows redshift dependence of the covering factor and Eddington ratio relation. If we limited sample at redshift less than 0.1, anti-correlation gets stronger, which suggests that discrepancy can be explained by difference in redshift. So, or let me summarize my talk. So my most important, my take-home message to you is that this one, agent polar dust emission may be an additionally important parameter to regulate structure of dust torus. All right, that's it. Thank you for your attention.
Thank you very much. I have questions on Slack. First one is from Dari. And Yoshiki, can you show us again the SIGALE parameter setting table?
Sure.
The asked if, because he found that the fractional AGN can be as high as 0.99. Is this possible or realistic?
Actually, a tiny fraction of our sample has agent fraction equal to 0.99, but this is again SDSS quasars. Some of them are really bright, typical agent. So in that case, actually few tiny fraction, but some of them still have that kind of really high agent fraction. So I believe that parameter range is optimized to our sample.
Thank you. We have another question from Tomo. So you got the polar dust information. How can that information correlate with the black hole mass or Eddington ratio?
Oh, that is very good question. Yes. So this one. So this green lines are actually covering factor of polar dust. So as you can see, even polar dust correlate with covering factor of polar dust correlates with borometric luminosity, black hole mass, and Eddington ratio. But actually, strength of correlation strength is actually I think the Eddington ratio and borometric luminosity has stronger than black hole mass, which means that agent polar dust could be driven by accretion, mass accretion rate or high borometric luminosity rather than black hole mass. I mean, these two quantities may be essential for regulate polar dust emission. from this figure. That's just the indication, yes.
So the correlation coefficient is smaller for polar dust?
Compared with dust covering factor, is not the case. But if we compare covering factor of polar dust between these three quantities, correlation strength of Eddington ratio is stronger than other quantities. This is the point.
How does the correlation coefficient compared with covering factor and then polar dust? I mean, dust tolerance and then polar dust.
That's a good question, but I did not yet study it. Yeah, that should be doable. Yes.
Yeah, but I mean, if by subtracting the polar dust, if the correlation coefficient increases, then that means polar dust the correlation coefficient should be smaller, right?
Yes.
But in this figure, it almost looks stronger, no, in panel A and C especially. So I'm a little bit puzzled.
I think yes, you are right. So correlation strength of polar dust is stronger than covering factor of dust torus. So this effect would this correlation much stronger when considering polar dust compared with without considering polar dust, I think.
Okay, thank you.
Okay, I think it's time to stop the discussion. You can continue discussing on the Slack. So before closing, let me once again thank the Galaxy Journal for enabling this conference. Thank you very much. And also, I want to remind all the speakers to upload your file. Some of them already did that, but if you have not, please do that so that we can keep discussing more on the Slacks. So please visit Slacks even after this session to add more questions or for the presenter to respond to the questions. Okay, so that is the end of the session. So thank you very much. The next session